Just
a couple of minutes maybe.
And I need you to enable the screen sharing too. So
yes, yes. Murli will do that.
Hi, Maria.
Hi, Manu.
Murli, maybe
Good,
you
how are
can
you?
wait for live streaming. You can wait until we start.
One second.
There is always some lag. I think that's fine. I think it's 6:31 here. So
Yeah, now it's live.
okay. So we'll start. Hello, everyone. I welcome you on behalf of Technologies for Low Carbon and Lean Construction Group here at IIT Madras. I am Piyush Shosali, faculty in Building Technology and Construction Management Group in the Department of Civil Engineering at IIT Madras. Most of you might be familiar with this research group, but I encourage you to visit our website for the updates. We usually have regular webinars by renowned researchers across the globe, and we have already conducted a few. And please get the notifications, and if you would like to work with us, we are always happy. So without further ado, let me introduce Professor Maria Younger. I think most of everyone should know her. It's my really pleasure to introduce her. She's a professor in the Department of Civil Engineering at University of Texas, Austin, in USA. She has a very interesting background. Her undergraduate degree is in chemistry from Duke, and then PhD in material science from Northwestern. And she worked with late Hamlin Jennings during her PhD, and she did then her postdoc at UC Berkeley before joining UT Austin in around 2002. So it's been around 20 years at UT Austin. She is quite active in American Concrete Institute. She has received a lot of awards. I will just name a few. She has received a Walter P. Moore Junior Faculty Award from ACI. Also, she has received Early Career Award from National Science Foundation. She's fellow of both American Concrete Institute and American Ceramic Society. She's a former chair of ACI Committee 236, Material Science of Concrete. And she serves on editorial boards of many reputed journals, including Cement and Concrete Research, Cement and Concrete Composites. So without further delay, I would now invite Professor Maria Younger to deliver a lecture.
Thank you so much, Piyush. I really appreciate it, and I appreciate the opportunity to speak to all of you today. It's a unique opportunity for me to have a global audience like this, and I think it's something that has been, more achievable now with Zoom and other types of platforms. So I appreciate that, and to see familiar faces too is nice. I'm going to share my screen.
Yeah.
And get this started. Hold on. Okay, you can see my screen now?
Yes, all
yes.
good.
Okay,
Yeah.
Great.
Thanks.
Hold on. Okay, I'm moving the videos out of the way so I don't see them. So what I'd like to talk to you about today is something that I'm working on. I've been working in my research for, I don't even know how long. I lose track of time now. So let's say 10 years, but I think it's less than that, actually, probably more like 8 years now. Which is looking at natural pozzolans and other types of materials as supplementary cementitious materials in concrete. And as I was putting this together, I gave a similar talk in a conference, the ICCM. Now, I don't remember what that stands for, but that was in June. I gave a similar talk on this topic in June, and I was thinking about it today in terms of an audience that's focused in India as well. And so while some of the topics that I'm talking about are very Western in nature, I want to make sure that we address currently what's happening in India as well. And so I welcome questions from you as we, at the end to bring it into that context as well, because I think much of what my thinking is, since I'm in the US and interact with people who are primarily from Western countries looking at supplementary cementitious materials, we tend to miss what's happening in other countries to a certain degree. And so I think that I would appreciate that sort of feedback and from you at the end. Okay. Before I get started, though, I want to talk a little bit about Texas, because Texas is very different than India, as you all know. So I live in Austin, Texas, which is the capital of this state. This state of Texas has just under 30 million people. It is the second largest state in the US by land, and I think the third largest by population. We are, in that sense too, just under 30 million, which is kind of like a large city in India, but is actually larger than many countries.
By any chance?
And also, when you think about it too, one of the things that I like to point out about Texas is, in terms of GDP, if Texas were a country, it would be in the top 10 countries in the world. So it's higher in GDP than Canada and Korea, for example, South Korea. So it puts things in context of when we're talking about a state within the US, and when we're talking about a university that's the flagship of that state. It's interesting to think of because it very well could be the flagship university of a country in that context. So the other thing I want to point out is on the left here, you see a picture of Austin. Texas is not all cowboys and ranches and dry things like you see in the movies. It's very green in Austin, and we have a river and some tall buildings, and the population is booming. So we get more tall buildings popping up. It seems like weekly, but I would say yearly. In our graduate program, so to tell you a little bit about our graduate program, we have about 350 students in our civil engineering graduate program. And those areas, those little boxes shown below, are the different areas of specialization that students can take. We added a new one a few years ago called Sustainable Systems to try to have a more holistic graduate program view. The ones in green tend to be a little more environmental and water focused, water and air focused. The ones in gray in the middle are the ones that are more structural engineering or materials engineering focused. And then we have construction engineering, geotechnical engineering, and transportation. I primarily have students who are in this infrastructure materials engineering program, and there's about 5 faculty or so that supervise students on concrete and asphalt type projects. The MUSE program, which is mostly computational engineering, is about 5 PhD students. It's much smaller, whereas structural engineering is our larger program, and we sometimes supervise students doing concrete research in materials from the structural engineering program. I just wanted to give you a sense of that before we get started, so you can get a sense of not just who I am, but where I'm coming from in the world and in the research that we're doing in Texas. So interestingly, I went to Google this weekend and I looked up supplementary cementitious materials in the images. I do this sort of thing sometimes. I look up green concrete, I look up all kinds of things just to see what Google shows me in terms of images. And 90% of the images that it shows me is the little array of SCMs from the Portland Cement Association textbook that has different colors of powders of SCMs. And that was 90% of the images that it showed. But I found this one, which I thought was going to suit my purposes much better than showing you powders of SCMs. And the reason is it is a graphical abstract. I struggle with the journals that ask for graphical abstracts because I'm not sure what they really are looking for, but I think this is an excellent example of a graphical abstract that basically is trying to demonstrate that we have supplementary cementitious materials with a variety of them shown here on the left. We add them to Portland cement as a replacement or addition, and we get changes in the concrete properties in terms of workability, microstructure, strength, durability, and we also get reductions in CO2 emissions, energy consumption, and the environment. And so this is a nice demonstration of why we use supplementary cementitious materials in concrete and what they actually are, just to get us started. So I credited the paper there for that abstract that I stole from Google. Okay. My primary interest in supplementary cementitious materials, while I really appreciate a lot of the durability aspects, I think we're really under a lot of pressure globally now to increase our use of SCMs, not just to increase concrete durability and improve mechanical properties, but really to play a big role in this, I would say in this picture here, in the darker purple reddish part that says reduction of clinker to cement ratio. So if we want to reduce direct CO2 emissions from cement production, we have a lot of different, what they call levers to do so. Some of it could be changing the thermal energy efficiency in the cement plant. You can switch to more lower emitting fuels. You can reduce the clinker to cement ratio, or you can use other innovative technologies like carbon capture. I would argue that These are all really important. However, they each come with a different pathway to get there and a different cost associated with that pathway. So the reason that I like to focus my research on SCMs is because it's something that I can do. I am not capable, as a material scientist and chemist, I'm not capable of actually going through and trying to make a cement plant more thermally efficient. That's a manufacturing issue, right? Fuel switching can be, depending on how you look at it, a mechanical engineering like thermal fluids or chemical engineering issue. It's not a material science issue. Carbon capture is a mixture of both manufacturing and technology, industrial technology in that way, and potentially a material science issue. But what we can focus, collectively our expertise on is this reduction of the clinker to cement ratio, because that falls within our wheelhouse of our expertise. And so that's one reason I choose to work on that aspect. The other reason is it's going to be that between all of these technologies, it's going to be pretty easy for us to implement supplementary cementitious materials where they are not implemented or where they're not implemented enough. So that transition of implementing the SCMs is pretty straightforward if you can find them, because we already know that they make our concrete properties better for the most part. So the implementation is pretty straightforward. We can reduce that clinker to cement ratio. Carbon capture, on the other hand, I think is critical, and we need to be working on this, but it's a lot more difficult to implement technologically and economically. And so we can reduce the clinker to cement ratio faster and sooner.
Sorry.
Likewise, alternative cements, I've worked quite a bit with alternative cements, including calcium sulfoaluminate cements and geopolymers. And I'm still working quite a bit with geopolymers. Those are harder to implement because it's a technology gap to actually use them. SCMs make concrete that looks like concrete, smells like concrete, behaves like concrete. It's all normal. It makes it easier to implement in the industry. Not to say we shouldn't look at the other things, but they're going to be further in the future. Okay, so one of the primary SCM that people use, hold on a second, I'm looking at the chat. Okay, please mute your microphones. Thank you, Ravindra. So the primary SCM that's used globally, the one that's used the most is fly ash. And so I was looking to see about what the use of fly ash is in India compared to other countries. So I found this article from the Times of India from August, and this is a direct quotation from that. It's literally a cut and paste, where India produces an estimated 226 million tons of fly ash annually, out of which about 188 million tons is being utilized, some of which is used as supplementary cementitious materials, so about 25%. So from this article, I want to contrast that to what's happening in the US. So this is a plot that I took from the Carbon Cure website, and the source is the American Coal Ash Association. If we look at 2018, so we look at the far right, and we look at the fly ash produced, that's about 35 million tons. That's only a tiny fraction of what you have in India. And we're using, a relatively similar percentage of what's being used. So the usage the usage percentage is similar, but the usage, but the production amount is much lower in the US, which makes sense for a lot of reasons. It's not surprising. I actually wanted to put a bar on this chart for India, but I realized I wouldn't be able to fit it on the PowerPoint slide very easily, because this scale only goes to 90. So if I had 226, it would go off the screen. So I thought that was really interesting for context. So India is in a very different position in terms of fly ash usage, even moving forward, than we are in the US, and in a different position than where we are in other countries as well. The US and many other countries can no longer rely on fly ash as their primary source of supplementary cementitious materials. And that's because there's a huge push to reduce coal burning power for coal burning for power production for a lot of reasons. The power plants are aging, and the repair and maintenance costs exceed the cost of building, for example, a natural gas plant or some other type of power production facility. And so that's one reason, especially in the US. In a lot of other countries, it's driven by environmental concerns. They don't want to, they would like to reduce coal burning power. And so we're in a position now where the we can't rely on fly ash because the fly ash production is going to decrease over time. And so a lot of the research that I'm interested in is diversifying those SCM sources so that we can reduce our reliance on fly ash for durability and for environmental concerns in concrete. And one of the ways I think about this, I think is a little bit different than the ways that some other people have thought about it. And I'm increasingly shifting my mindset to this point of view is I don't want a great SCM. I don't want the best. We don't want to be number one. We want to be just good enough. And so that's the focus of this talk is when we're looking for a material, we want a material that is just good enough. And I'll explain why in a few more slides. And the other thing in terms of cost, so much of our concept of cost with respect to fly ash and with respect to using fly ash in concrete was often framed in the concept of fly ash being cheaper than cement. I would argue that if we can find SCMs that are just cheaper than carbon capture, which is our next best option for reducing CO2 emissions, then we're doing pretty well. We need to reframe to not, is it cheaper than cement, to, is it cheaper than other alternative ways of reducing CO2 emissions? That's a bit of a stretch. That's pretty expensive, but I think that's something that we need to be starting to think about. The good news when it comes to trying to find replacements for fly ash is not a great SCM. It is not a high performer. It is a mediocre material. The graph on the left comes from work from Deb Glosser, who was at Oregon State University with Burkan Izgor and Jason Weiss. And they have a method where they look at the heat released in a Pozzolonic reactivity test they have versus calcium hydroxide consumption in that same sort of paste system using TGA. And then they plot it versus thermodynamically derived reactivities for pure silica and pure alumina systems in this plot that you see here. And so when they take fly ashes and put it on this plot, you can see that all of these materials, these different fly ashes in these different shapes, all fall between 20% and 40% reactive. That means that 60 to 80% of the material in a fly ash is inert. So we're looking at a material that's not a highly reactive material. The plot on the right comes from one of my students' works, Saif Al-Shmaisani, one of my former students' works. He finished his dissertation in 2020. And this is using the R3 reactivity method that's used to assess the reactivity of SCMs. And I'll go more into that later. But if you just look at this plot, this CA is a C fly ash and the FA is a F fly ash. And it's not, compared to other materials that were tested, it's not the best. So if we're looking at, and I'll show, again, more of these data, we'll take these apart later. But when we're trying to replace fly ash as an SCM, the bar is low in terms of performance of the material. We're not trying to replace a great material with a great material. We're trying to replace a mediocre material with a mediocre material. And that's promising in terms of evaluating sources. So, in terms of research questions that I want to talk about today is assuming fly ash is our reference SCM. We're trying to replace fly ash in concrete mixtures. We don't need great performance from what we're trying to use to replace it. We just need it to be as good as fly ash, and people will be pretty happy with the performance of their concrete. The other point to think about is it is better to use from an environmental clinker cement to clinker ratio reduction. It is better from an environmental perspective to use a high quantity of an average performing SCM than a low quantity of a high performing SCM. We want to reduce the amount of clinker in our cement, which means we want to have a high amount of SCM in that system, which means we don't need a really highly reactive material to get there in a small quantity. So think silica fume in 5 to 10% doesn't really get us much in terms of clinker production. Fly ash in 30 to 40% is better. So that's where we're heading here. So what this opens opportunities for is, and I'm going to talk about today, is impure natural Pozzolans. So how do we get these sort of less pure materials that aren't so great, they're mediocre? How do we get these less pure materials to work in our concrete mixtures? And then also blends of materials, blends of natural Pozzolans with fillers, for example, cold combustion products that are underutilized and other materials to create these sort of tailored bad materials. I won't say bad, tailored mediocre materials. Let's aim for the middle. So in terms of natural pozzolans, and I don't know, we can talk about later what sources of natural pozzolans are available in India and other regional countries there. In the US and in many other parts of the world, we have some deposits of volcanic natural pozzolans. And so the one shown here on the right is in Arizona in the US to a quarry that I visited in 2019, I think. And this is a pumicite type deposit. And so you have these volcanically derived minerals like pumice, perlite, volcanic ashes, and zeolites, or you have sedimentary pozzolans, so calcined clays and shales of various compositions, including metacalins. And so the sedimentary pozzolans are known to be more prevalent globally than the volcanic pozzolans, but both are considered natural pozzolans. The general thinking up until recently is that natural pozzolans aren't necessarily great materials to use as SCMs because they're only regionally available. They're not widely distributed. That's changing. What is slow to change is the commercial availability of these materials. And so many of these are easier to obtain for research purposes than they are to obtain for actually making concrete mixtures. That'll change with time as well as the market matures for these materials. What I want to talk about today is not these, really nice, pure, clean, natural pozzolan sources, but I want to talk about the stuff that the quarries are throwing away. So for example, overburden materials, we'll talk about that. So you can take, again, a waste product of an industry, but a waste product of a natural pozzolan industry. And then also blending materials to try to optimize that mediocrity. Okay, so I'm going to go through some case studies from our research. These are all taken from different types of projects to demonstrate what I'm talking about here. So the case study number one is what I would call an impure pumice. So pumicite's used for a lot of different commercial products. For example, every time you have jeans that you wear, most of those are washed with pumice. Pumice is used in cosmetic products, is used for a lot of different industrial purposes. Most of what's sold in terms of pumice is a sort of pure white material. And that's what the other industries like. But in order to get to that pure white material in a quarry, if you look at this quarry, this picture I just stole off of Google search. But if you look at this type of quarry, for example, you see that the top layers aren't so white. And that top layer for an industry that's looking for a pure white material is not desirable. And so they actually stockpile it and discard it. So you take something that's a quarried material and it has a byproduct too. Its byproduct is overburden, is what they call it. So if you look at these two buckets at the bottom, the one on the left is a more pure pumicite. The one on the right is an overburden pumicite. It's more tan colored. And so what we're interested in is we know the pure pumicite works great as an SCM. How does the tan one work? We can get that one cheaper. That's a byproduct material that nobody else wants. Can we use it for our industry? It's a different composition. It's about 74%. In this particular example, it's about 74% amorphous, whereas the pure pumice is about 93% amorphous, but both have similar silica and alumina contents. You could run through this same case study for perlite, same exact sort of process of thinking about things. They also have overburden. In terms of evaluating these materials, one of the first things that we do in our lab is we run the R3 test, which started out being called R3 because it's called the Rapid, Relevant, and Reliable Test, a very optimistic name. And it's now standardized under ASTM C1897. So these mixtures consist of mixing your supplementary cementitious material with a potassium sulfate solution, calcium hydroxide, and calcium carbonate. And then you have two possible means of analysis, only one of which I'm showing here, which is measuring the heat release using isothermal calorimetry over a 7-day period. You can also measure bound water and curing it at 40 degrees and measure the bound water using a furnace, which is simpler. And actually the industry prefers to do that. In the labs, we prefer calorimetry. And then the industry, that if they don't have a calorimeter, they prefer the bound water method. As I mentioned, Jason Weiss's Pozzolonic reactivity test is a very similar test, but at a different solution composition and a higher temperature. So there's a couple of tests like this that are available out there. And so when you run this test, you get, in this particular case, the heat released, the 7-day cumulative heat in joules per gram of SCM that was run in that calorimeter for 7 days at 40 degrees C. When you run this test, you get different values. The higher the value, the higher the reactivity. So this these gray materials here on the left are quartz, which is Q here shown, and titanium dioxide. You expect that these are not pozzolonic, so therefore they have no heat. So that's really just a check against an expectation. If we look at the fly ashes, the CA and the FA that I showed earlier, and we look at the pumices, the PP, again, silly names, but this is what they have. PP is pure pumicite. PI is impure pumicite, so the overburdened pumice. They actually have a very similar reactivity to the class F fly ash in this particular test method. So it's really not so different in this particular test method, and the impure pumice is not so different than the pure pumice, which is promising in this test method. Another thing we like to look at is compressive strength. These are compressive strengths of mortars according to ASTM C109, and we took 25% of the cement replaced with the SCM. And what you can see here, the black columns are the Portland cement, and the reference is relative strength as 100% of the Portland cement at that particular age. The dotted lines are an 85% line and a 75% line, just to get a sense of what you would expect these types of materials to do. If you look at the fly ash, it's above the 85% line, but not as high as the Portland cement by 28 days. If you look at the pure pumice and the impure pumice, they end up being actually quite similar to the Portland cement at 28 days and higher than Portland cement at 90 days. So they're actually outperforming a class F fly ash in compressive strength, which suggests that from a performance perspective, at least with respect to strength, they're good substitutes for fly ash, better than fly ash. Another thing we often look at is how these materials control expansion due to alkali-silica reactions. So how do they impact durability? In this particular test, this is the black is the control, the aggregate with just straight Portland cement, and all of the pure pumice, the overburdened pumice, and the class F fly ash all reduce expansion below the threshold in that particular 14-day rapid test method, accelerated mortar bar test. So they all behave similarly in terms of durability. We have more data on this. I'm just showing examples here, but from all of the testing we've done, this overburdened pumice material is a lower cost alternative to the more pure material, but the performance is quite similar in spite of the small difference in amorphous content. The control of ASR expansion is excellent for both. There's some concern in the community about the alkalis present in these natural Pozzolans because their alkali contents are pretty high, but we've shown that it doesn't affect their ability to control ASR because these alkalis are not soluble. So they're really quite good materials when you're looking for replacement of a fly ash. Okay. Another case study that I want to bring up is something that I'm pushing quite a bit right now in the US, is the concept of an impure metakaolin. So we know that metakaolin is a highly reactive Pozzolan, but it's used in really small amounts because it has a high impact on the workability. And as I mentioned earlier, we don't want the 5, 10, 15% replacements in terms of clinker to cement ratio. We really want higher replacement levels to reduce the clinker contents in our cements. So this 15% isn't good enough. In the past 12 years or so, there's been an increasing body of work on impure clays. Some of these contain different clay minerals like montmorillonites and bentonites, illites, and some of which increasingly just contain crystalline impurities such as quartz and other mica and other minerals. So I would say that all of these types of materials are worth investigating and worth sourcing for concrete mixtures. The particular example that I'm going to show you today is a commercially available pure metakaolin type material that's compared to an impure metakaolin material that's primarily quartz mixed in with metakaolin. So it's not a reactive material. And you see the difference in amorphous contents there of 99 versus 77%. And I have some other materials I'll show you as well, but in this particular case study, I'm focusing on these. So when we talk about workability, this is a good imaging graphic demonstration of what metakaolin does to the workability of a concrete mixture. This is actually a mini slump test on pastes. It's not a concrete mixture, where the mini slump cone diameter is 40 millimeters at the bottom, and the height of the cone is 60 millimeters. And if you replace Portland cement with a relatively pure metakaolin, you get a very, very low slump, which is expected. Compared to the Portland cement shown here, a class F fly ash, which has a greater slump spread. We measure the spread, not the height, generally in these mixtures. And then this sort of moderate purity calcined clay, something similar to this 77% amorphous material, ends up having a mini slump spread very similar to Portland cement. So you are moderating this problem with workability by reducing the purity. So that's promising. The other thing that happens with this is, of course, if you reduce the purity, you reduce the reactivity. So this is the R3 test again. The MP is the pure metakaolin, and the MI is the impure metakaolin in this plot. We can see that both of these, even the impure one, are much more reactive than other SCMs. They're much more reactive than these pumices. They're much more reactive than the fly ashes. And so these materials are, even when you make it less pure, you still have a greater reactivity from that material. And when it's 77% amorphous. I have other examples here from another research study. This is from my current student, Caitlin O'Quinn, where she's looking at a lot of different impure metakaolin sources. The ones that say C are commercially produced materials. So this is a CK99 as a commercially produced 99% pure metakaolin material, whereas the L ones are ones that are calcined in the laboratory. So LK25 only has about 25% metakaolin in the system. So what I wanted to point out from this work is fly ash, in terms of reactivity in this R3 test, is really low. You can have a calcined clay with 25% metakaolin, and its reactivity is pretty similar to a fly ash. You don't need a really pure material to try to hit that bar of expectation when you're replacing fly ash. Actually, in fact, 25% is plenty if that's your goal, if your goal is to replace fly ash. So that's something to consider. Does that mean you have to go and look for sources that naturally in a quarry only have 25% kaolinite? No. I would argue that you can start blending these with other materials that are inert, similar to this, to the LC3 system, but it doesn't have to be limestone. It can be quartz, it can be other natural minerals. You can start blending to reduce the purity of this kaolinite in order to create a material that hits your targets in terms of workability and reactivity. Again, if we look at compressive strengths, this is the same plot shown earlier, just looking at the metakaolins in these. So the metakaolin at 28 days is significantly higher than the fly ash and the OPC, and even the impure metakaolin is higher than both as well. So these materials are certainly sufficient and adequate for replacing cement in concrete, and will provide good performance. There's even, and this comes from work from Francois Ave and Karen Scrivener, but I think this, to me, this plot is really meaningful, so I'm sharing it with you because I think this is an incredibly valuable plot. So what this plot shows you is Portlandite content versus calcined kaolinite content. So if we're looking at something, for example, that has a 25% kaolinite content versus, let's say, a 90% kaolinite content, that's what this x-axis is, and the colors are at different ages. So what becomes really clear is that the consumption of calcium hydroxide by the SCM pretty much tails off at 50 or 60%. There's no reason to ever go higher than that because you're not able to consume more calcium hydroxide in that system. You hit a wall. The other thing to note that I think is even more important is this degree of hydration of clinker versus calcined kaolinite content. If you look at the 28-day data, as you increase kaolinite content, your degree of your hydration of clinker reduces. So you're actually not optimizing your system. You're actually reducing the effectiveness of the cement to hydrate by adding more higher purity kaolinite. So having a lower purity kaolinite allows your cement to hydrate fully. So again, pushing for this concept of lower purity is better. It helps workability. It helps, you get adequate strength, but it helps optimize the efficiency of your system as well. It also saves money. If you use less pure material, no one else wants it. In the other cosmetic industries and other higher dollar industries, we save money. We increase availability because we can explore wider variety of sources that other industries aren't using. And we can still get the benefits that we have from other, from those systems. Okay, the last topic I want to talk about is blends with cold products. So when we talk about the use of fly ash and the production of fly ash, we're often just talking about fly ash. We're not talking about the other products that are byproducts of the cold combustion process. And so, for example, there's a material called bottom ash. We have fluidized gypsum desulfurization ash. We have other types of materials. Economizer ash is another one that come out of these power plants that we're not using in concrete. We also have fly ashes that don't meet specifications. So for example, in the US, ASTM C618 that specifies fly ashes has boundaries on a lot of things in the fly ash, including the sulfate content and the sum of oxides and other types of properties, chemical properties of the material. And so right now, those are not allowed to be used in concrete under ASTM C618. It doesn't mean they're not allowed. You can always go off spec. But according to the specifications now, these are not allowed materials. The other interesting issue we have in the US is that the Class C fly ashes that have higher calcium are now the considered less desirable in terms of materials to use in concrete mixtures because they don't assist with our workability, with our durability of concrete as much as Class F fly ashes. So they are less used, which means they are more highly available. Another interesting issue when we start considering the reduction of availability of produced fly ash because of power plant decommissioning is all of the fly ashes that are in ponds and landfills that are come to be known as harvested fly ashes. So they're harvested from a pond or a landfill. They have to be processed somewhat. And these are being explored too as alternatives to fly ash and concrete. What we have been looking at and what other people as well are looking at is not just looking just at these materials, not just looking at bottom ash, not just looking at off-spec fly ashes, not just looking at harvested fly ashes, but what happens if we blend these? So if you're harvesting anyway, you already have to dry and grind it. Why not blend it to optimize it and sell it as a product that's more highly processed or engineered or optimized? So we have this great opportunity to not just take a product as is, because that's the cheapest way, but actually to optimize the performance of our products and to expand the resources of what's available by blending and processing. So that's what I want to address today, and just with a few examples. So one example is milled bottom ash. So bottom ash from coal power production is the material that falls to the bottom. It has a lower amorphous content than fly ash. In this particular example, the amorphous content of this bottom ash is about 66%, and the amorphous content of the fly ash is 83%. The bottom ash has a lower reactivity. So again, aren't you just so impressed that I keep showing the same graph over and over again? I just keep dumping the same material at you, but highlighting different aspects of it. Okay, so this is the fly ash FA, is what we've looked at before. This one that you were probably curious about before, the pink one, is MBA. That's a milled bottom ash. So this material is less reactive than a fly ash in this R3 test. It is actually on the borderline of what RILAM's recommendation is for calling a cutoff between being inert and reactive in this particular test method. If we test it for compressive strength, again, this is 28-day strength, not 90-day strength, but if we look at the Portland cement black being the control, they're slightly lower than the Portland cement, the Class F fly ash and the milled bottom ash. They're somewhat lower at 28 days. They are still greater than 75%, and the Class F fly ash is about 85%. So again, if we were just going to take this particular milled bottom ash and call it a replacement for fly ash, you might say, it's not really good enough. It's not, our bar for fly ash is pretty mediocre. It's not meeting the mediocrity standard. We need something better. And so what you can do, for example, is you can blend it. So in this particular fly ash, this is a R3 test as well, a cumulative heat of fly ash. This is a milled bottom ash in red, and this is a blend of 60% fly ash, 40% milled bottom ash. That blended material suffices in terms of performance. It suffices in terms of strength. And so you get a better material by optimizing your resources through blending. Where you do have to be careful is what are some of the other consequences of blending. So what I'm going to present next is a little bit of a cautionary tale. For the most part, anything we've done with blended materials in our lab, whether they're blended by a commercial producer or blended by us, the vast majority of the materials work beautifully. They are great opportunities. What I'm going to present, and I'm cautious to do so because it's just these tiny little drawbacks. I don't want you to come away thinking that blending is bad. Blending is good, but there are some things that you need to be careful with. And so that's what I'm going to talk about next. One example is if you take a natural Pozzolan and you blend it with a fly ash, you can get a blended Pozzolan ash material. And so this is an excellent opportunity to kind of optimize and engineer your blends for performance by taking advantage of available resources. So these are SEM images of a natural Pozzolan, a fly ash, and this particular blended material, which you can see has rounded particles and angular particles mixed together. What happens in this case, which is not surprising at all, is if you look at the these particular materials in a rheology testing, where you're particularly looking at the slope of the material, the slope of the line as an indication of viscosity, and the y-intercept as an indication of yield stress, that you can see that these mixtures, you have an OPC, you expect that a fly ash will have a lower yield stress because of the rounded particles. And what you see is that if you mix a fly ash with a natural Pozzolan, you remove that beautiful effect of the spherical particles by mixing it with an angular material, and you actually increase the yield stress of the materials. So it's pretty obvious if someone sells you a fly ash that's a fly ash mixed with a natural Pozzolan, in that the workability of your concrete mixture will change. And so I'm only saying this because it's expected, but it's something to look out for if these materials become more prevalent, that it doesn't behave like a normal fly ash would, especially in terms of workability. You lose some of that benefit of the spherical particles. Another thing that happens when you blend materials is that you may not get rid of all the problems associated with the original material. So this particular example is showing what happens when you take fly ashes that are that don't meet the specifications. So where it says RM on these axes, these are RM means remediated in this particular coating system. So these are 3 different fly ashes that have been remediated, in this case remediated by mixing with a natural Pozzolan, so you can change their composition. And by changing the composition, you can meet a specification. If you look at setting time, the thing that draws your eye in this picture is this crazy green line. This particular fly ash had a high sulfate content originally and was out of spec because it had a high sulfate content. If you blend it with a natural Pozzolan that had no sulfates, you can get it to meet the specification and reduce that sulfate content. You dilute the sulfates that are in there, but you don't get rid of the problem caused by the sulfates, which is a delay in setting time. So the cautionary tale here is, just because you can meet a specification in terms of composition doesn't mean that you've gotten rid of the performance problems from that original material. The other problem we've encountered, for example, and I don't think I have data on this, so I'm going to go ahead and talk about it on this slide, is if you have a class C fly ash that doesn't protect well against sulfate attack because it has C3A and other cementitious phases in it. If you blend that class C fly ash with a natural Pozzolan or with a class F fly ash to reduce its calcium content, you blend it to try to meet a class F specification. So you're reducing the calcium content of that class C fly ash just to be able to use it. It still won't protect you against sulfate attack because that C3A is still in there. Even though there's less of it, it is there. And so it complicates our need to characterize these materials and understand them better. We can't just use our current specifications that are just based completely on oxides. We have to be a little more careful, and maybe it requires that we do X-ray diffraction to look at the type of sulfate that's in the system, to look at the type of C3A that's in the system. Because once we start blending, we have a lot more unknowns, and we have a difference in way things behave than the way they were originally. So I think we have a lot of opportunity to start blending and mixing materials, not just natural Pozzolans, but even inert materials with cold combustion materials and other products to expand our resources of what we're using, take advantage of everything available. But we have to be careful with rheological behavior. We have to be careful with the sulfate content and the C3A content, which may necessitate changing specifications to demand X-ray diffraction, which in the US in C618, they do not currently require. So it's something to think about moving forward. Okay, so in conclusion, I think we need more supplementary cementitious materials, and we need to get them creatively by taking advantage of resources that are available and trying to optimize the use of those resources, but not optimize for high performance, optimize for medium performance, because then we can use more. We need to be careful about workability, setting time, durability. We need to be careful about characterization. We need to be really careful with specifications. But we have a huge opportunity here to get more creative about our sources of supplementary cementitious materials and how we produce and use them and optimize them for our use. And this includes cold combustion products and also includes natural Pozzolans or whatever else comes out there, ground glass and other materials as well. So I think we have a lot of opportunities, but we also have a lot of challenges in terms of commercial production, but also characterization and specification. I want to conclude by thanking funding from the Texas Department of Transportation for several years, from the National Science Foundation, and EPSRC in the UK for a joint project we have on looking at carbonation in concrete with supplementary cementitious materials, and this is in conjunction with Susan Bernal at Leeds. My current student, Caitlin O'Quinn, and former students shown here, and collaborators, and then also that in the US, the Natural Pozzolan Association, who has been extremely helpful in providing materials and resources for us as we do our work. So thank you very much, and I'm happy to take questions.
Thank you, Maria, for an excellent talk. We have time for questions. So those who are here, please unmute and you can ask questions.
Can I go first, Piyush?
Yeah, go ahead.
Oh, maybe I'll let Jan go first.
Okay.
Jan is here.
Yeah.
Well, thank you. Good morning, Maria.
Hi, Jan.
Presentation, very, very informative review. I really enjoyed it. The question I have is regarding the workability of low purity Pozzolans. You said that low purity Pozzolans are actually helping with workability. Could you explain what the mechanism for that would be? Because I assume they are probably having the same fineness as high purity, or is that incorrect?
So I think there's two things to think about in terms of workability with these materials. So when we're talking about the low purity Pozzolans and the workability, it's specifically the calcined clays. The pumices, for example, and I think I had a slide in here, but I don't want to be flipping through and finding it. But the pumices, if you change the purity, it does not change the workability very much, unless you're changing the purity by contamination through, for example, a bentonite clay that might actually negatively impact water demand, right? But with the metakaolins, the reason the metakaolin materials have such a strong impact on workability isn't just the particle size distribution, it's the shape of the materials. So these clay particles are very, very fine, but they're also plate-like, and they affect the workability because of that. But if you have, for example, a kaolinite mixed with a quartz, the quartz particles are, they're not round, but they are angular, but they are not as fine. So your overall particle size distribution could be slightly coarser, but really it's that mechanism of the plate-like particles versus the more angular particles, or the more rounded particles, I would say, rounded angular. Does that make sense? Of a quartz,
Yes,
a finely
yes.
ground quartz. It's changes your workability significantly. And so, it depends on what your impurity is with the clay. But most of the ones we look at, they're naturally contaminated with crystalline materials. So if they're naturally contaminated with the montmorillonite or illite or other types of clays, you're going to calcine those anyway. It's different. But in the US, much of our lower purity metakaolin production sites are contaminated with inert crystalline materials. And I would argue that we should actually continue that practice even intentionally for the more pure materials, intentionally contaminate them with crystalline materials to help the workability.
Great. I assume that will also probably influence positively shrinkage and other volumetrics.
Yep.
So, all right. Thank you.
And we've looked at shrinkage a little bit with these materials. I don't get super excited about shrinkage. And maybe I should get more excited about shrinkage. But one of the things that I've noticed is with shrinkage, at least in my mind, it's completely related to degree of hydration or degree of reaction. And so if you look at shrinkage, if you control the water cement ratio and you control the degree of hydration for when you start the shrinkage test, if you control for both of those, you don't see much difference in shrinkage. But the problem is many of our standards require that we change the water cement ratio to adjust for workability. And then of course you're going to see differences in shrinkage. But when we measure shrinkage versus mass loss of water, we don't see a lot of differences in shrinkage with these different materials.
Thank you very much.
Mm-hmm.
Maria, thank you for a very comprehensive presentation on several alternatives that we can actually explore. I was particularly interested in the statement that you made that we can probably look at higher replacement of more mediocre Pozzolans as against smaller replacements of high purity Pozzolans. And I think that's a very important thing to realize. But it's okay from a materials perspective or from a concrete technologist perspective that we think about it this way. How do we go about convincing the structural consultants, which is a much bigger or much more difficult aspect to really think about? Because, I mean, have you had experiences with, let's say, the Texas Department of Transportation, where you've tried to look at implementation of some of these strategies? Because
so I would say, there's a lot in that question, right? So I think it completely depends on where you are and how conservative the structural engineers are. Right. So I would say in Texas, there are, at least in the Texas Department of Transportation and other agencies in Texas, they allow a relatively high volume, of SCMs because of durability specifications or mass concrete heat specifications. They have certain situations where it's actually written into their codes that using SCMs is good. Whereas in other places, they're more conservative because they haven't adapted that type of model yet. So I would say that, thinking about it globally, I personally like the European model where they blend the material and sell it as a pre-blended material, because it takes that control away from the engineer. If it meets the performance and it's already in there, it's going to be a far easier sell.
So you're talking about blended cement itself rather than using
so if you have the blended cement itself, we don't do that in the US. I don't know in India if you do it that way or not.
Yeah, in India, primarily we use fly ash based Portland Pozzolan cement and then a slag cement. But there is still quite a bit of on-site blending or admixing into the concrete that goes on.
Yeah. And I think, you know, it depends on the industry, but I think that if in the places that are resistant, it's going to be better to use a pre-blended material because they don't know what they're getting. You know, they can't say no because that's what they're receiving, right? I had a conversation last week or the week before, I think it was last week, with someone who is in a country that they don't use SCMs at all.
Okay.
And one of the reasons is they don't have silos for SCMs. And they don't have SCMs produced in the country, so they're reliant on their cement producers to decide to ship it. So it's not even an issue with the structural engineers not allowing it. It is completely an issue of just the system not being mature enough to accommodate the use of SCMs. And so I think, you know, in that sense, my mind goes to it's the cement companies that are providing the cement to the ready mix producers. It is their responsibility to reduce their clinker to cement ratio in whatever means they can. And if the silos are the limitations, provide a pre-blended material. So, you know, we can think that in the research lab, we have all the answers. There's a lot of complications in the field that the obstacles in the field, but I think SCMs are easier to implement than a geopolymer or a, you know, magnesium phosphate cement or something else. It's going to be this is our first hurdle. Yeah.
Just one more question regarding natural pozzolans. So is there some sort of a directory available in the US where you can actually locate useful sources of natural pozzolans? Because in India, we don't have a good idea about where our natural pozzolans are. In fact, we undertook a research project where we investigated ash that flew from a volcanic eruption in Indonesia, the Toba ash, basically. Yeah. And it's there was a nice deposit that we found in the state just north of here. And we found that the ash had fairly good pozzolanic characteristics, but we don't really have a control on where it is obtained. But do you have something better in the US?
So what happened here, and again, with COVID, my sense of time is really messed up, but I think it was 2017, it could have been 2016, that several of the producers of natural pozzolans in the US created this Natural Pozzolan Association. Okay. And what that facilitated is, it facilitated a lot of things. It facilitated communication in the industry about best practices. It consolidated information about resources and what's available where. It helps people who are trying to get a deposit explored and marketed. It helps them have a group of others to interact with. So I would say generally, it's been a positive thing. It's still pretty small, but they can advocate for their needs and they can also serve as this source of who's providing what where. It doesn't mean that all producers are part of the organization, but many of them are, or at least they know who their competitors are. And that's made all the difference, because before that, we were calling, when we first started, we would find something on the internet of somebody who might have had a zeolite source who would tell us about their friend who had, it was a mess. Yeah. And this has changed things considerably, having the association.
That's great. Thank you, Maria.
Yeah, but it means they have to sell it. Like a lot of these people in the association still aren't, they have a deposit that they're testing. That doesn't mean they're selling it.
Of course.
And that's the other part that where the research is ahead of the industry, of the commercialization.
Correct. Thank you. Thanks, Maria.
Thank you.
We have time for a couple of more questions. Please unmute yourself and ask your question. I have just a couple of questions. So thanks, very interesting talk, Maria. One thing is, what's the state of work on biomass ash utilization in states, and what's your opinion on that?
My opinion or knowledge of that is that it's still research focused. And even I spoke to someone at the ACI convention a few weeks ago who's been working with a biochar ash. I'm not aware of anyone really actually commercially selling it. Even years ago when they had rice husk ash and there was a producer in the US, but that producer ran out of materials and hasn't sold since. So I think it's still an immature industry. I think it has potential. because the research is there to show how you can pre-process the material to reduce alkalis and increase silica content. It's all there, but somebody has to decide that it's cost effective to make it and sell it. And I think that's our hurdle. So at least from my like policy perspective point of view, going back to that point of, is it cheaper than carbon capture? Carbon capture is really expensive, right?
Yeah.
And if the industry goes to the point where they are exploring carbon capture, they should explore more expensive SCMs too, because those most expensive to produce SCMs are still going to be cheaper than carbon capture, and they're going to work. But as Manu was suggesting, we need a system that enables them to be distributed and used commercially efficiently, which is hard, but it is still cheaper than carbon capture.
Yeah.
And I still think carbon capture is a good idea.
Yeah. From India's perspective, it's because we have a lot of agricultural residues, so a lot of biomass ash is there. So a lot of work is going on in India right now to utilize biomass ash, Portland cement and non-Portland cement based systems.
And is there somebody selling it, or is it just in research still?
Yeah, it's still in research state.
Yeah.
I mean, rice as
Yeah.
cash is commercially sold because it is allowed. So
I would say where we've made progress in the US is that ground glass, recycled glass, is now commercially sold, at least in the New York region of the US. So in that northeastern part of the US, there is a supplier of ground glass Pozzolan. So we've made progress on that, which is good, because again, that's something that was taken from research to a specification to commercialization. And it could expand beyond that too. But we haven't, I don't know of any biomass ash producers commercially right now. And I think really it's a cost limitation.
Other question is about the impurities. So it's great that we should start using this impure material. And have you looked into the leaching part? Sometimes the concern is like for long term, what is the potential of leaching, like depending on alkaline, alkalis or heavy metals present in these systems?
It's interesting that you ask that, because we've been doing actually a lot of work on leaching, separate from this, primarily from stabilization of. We first started with stabilization of fly ashes, for example, what they call the trona impacted fly ashes, which have higher alkalis and are more soluble. They can't be used in concrete, so they have to dispose of them. So we've looked at trona impacted ashes, and now we're looking at brines we're using fly ashes, for example, to stabilize brines from coal power and from oil and gas production. So we have these wastewater residuals that we're solidifying with fly ash, lime, cement. And so we've been looking at heavy metals from all of these systems. Beautifully, even if you alkali activate them, you mix them with Portland cement, you mix them with lime, it's such an amazing system for capturing heavy metals that generally in everything we've done, there's some exceptions, but for the most part, in everything we've done that's fly ash based, you are capturing these heavy metals, and there's below the leaching limits from any sort of specifying organization. We haven't done this with natural Pozzolans yet, but we did do a study years ago where we looked at radon emissions. So it was gas, not leaching in water, but gas emissions from fly ash and from metakaolin. And the student at that time, and this is really interesting, because you think of fly ash as being this nasty material. It's this byproduct of coal. And you think of metakaolin as being this pure white, beautiful powder.
Yeah.
So metakaolin must be healthier, right? Because it's so clean looking.
Yeah.
It turned out that the radon emissions from the metakaolin source she had were much, much higher than what we were getting from fly ash. And then we got a different metakaolin from a different geographic region, and they were lower. So a lot of these types of things are really going to be based on the mineralogy and the geology of where things are deposited. And so we haven't looked at it in natural Pozzolans, but it's something that should be examined. I think the reason it's less examined than it is because once you put it in concrete, it's all stable anyway. Like even the radon from the metakaolin and the fly ash, I don't want to make anyone nervous. It's all fine once you put it in concrete. The problem goes away. And so I think that, at least from my perspective in the studies we've done, it is something that we should look at, and we haven't, but I don't anticipate it would be any worse than fly ash.
Thanks, Maria. The last call for the final question, if anyone would like to ask. Yes. Yeah, please go ahead. Yeah.
I'm Hemalita from CRC. It's a nice presentation. My question is on when we are using milled bottom ash, what is the percentage of unburned carbon content present, and what is the influence of the carbon content on the reactivity or pozolonic action?
That's a good question. And so in this particular material, we measured loss on ignition to get a sense of the unburned carbon content. And it was not, in this particular source that we looked at, it was not very high. It could be, right? So that's certainly a potential. And again, this is what becomes kind of interesting in terms of opportunities moving forward, that people who have sources, companies that have sources of fly ash with high unburned carbon, can do one of two things. There's the processes that are being used in the US, and I'm aware of one that's in Pennsylvania and one that's in Florida, so on the East Coast, where they're actually igniting the fly ash to burn off the unburned carbon before they sell it and distribute it. So they can do that, right, if they have a problem. The other thing they can do is they could just blend it. So if you need to be below a certain loss on ignition, you could blend it with something else and reduce that loss on ignition, like blend it with the fly ash, reduce that loss on ignition. But I think the question is then, if you do that, is that the best option, in the sense of, is it, you need to check to make sure that by dilution, you're actually diluting and not simply pretending to hide the problem. Yeah. But in the one we looked at, it was fine, but I foresee other problems with other available materials. And I know that Jan Olek on the call has looked at a greater variety of sources of bottom ashes. And he may have, I don't know if he wants to chime in here about the unburned carbon and his sources of materials.
Yeah, we didn't find it to be a problem, actually. When we were looking at the ability of those materials with respect to having air-entrained concrete, we did not notice the need for extra air-entraining agent. In many cases, it's really not so much the unburned carbon as some of the maybe other minerals like carbonates that also contribute to this loss on ignition. So it typically is not, we didn't find it. We look at 3 different sources, we didn't find it to be a problem.
Thank you.
Okay, I think we have come to the end. Thanks again, Maria, for your time and excellent talk. I think most of us got benefited, and also this will be available on our YouTube channel, and I will share the link so you can also share with others. And thanks again to all of those who have attended. I think we had people from different countries, at least few, so that's great, and we expect your same level of participation in future webinars. Once in a while we'll invite renowned researchers in this domain, and they will share their experience. Thanks again, and thanks, Maria.
Thank you.
Thank you, Maria. It was a pleasure.
Thank you.
Thank you. Thanks, Jan, for also joining.